Today we're going to start chapter 6.3. You're skipping over chapter 5 because you've covered it in Algebra 2. And so we're going to go to chapter 6.3 and we're going to talk about vectors. If you're taking physics, you've already studied vectors, but not everybody is taking physics or has taken physics. So we'll start from scratch here. Some quantities that we study in physics and calculus are represented not only by some number, okay, the number is called the magnitude, but also by a direction. All right, so we have a magnitude and direction that we're going to represent some quantities with. Example of these quantities are velocity and force, two examples. All right, velocity has a magnitude and a direction. The magnitude would be the speed of an object, and the direction would be whatever direction the object is traveling in. And similarly, the force, the magnitude is how much force you place on an object, but it also has a direction, the direction that the force is being applied. So to represent them, we use a directed line segment. A directed line segment. And a directed line segment has an initial point and a terminal point. Initial means start, terminal means end. So a directed line segment might look something like this. So we'll have the initial point A, the terminal point B, and that is called a directed line segment. It has a magnitude. The magnitude is the length of this line segment, and the direction is whatever direction it's pointing in, and it has to do with angles, so we'll talk about that in a bit. But the length of this is called the magnitude. Now, everybody took Algebra 2 last year, so in Algebra 2 we had forces applied to an object, and when we were talking about a force, we talked about the magnitude, which was the length of this. And the magnitude of this, you have a double line, vertical line, and then you have the initial and terminal point. So that is how you represent the magnitude of this. And the notation for this is an A, then a B with a little arrow over the top. You can close up this arrow, or a lot of times we just put a single arrowhead on the top. So that's the arrow. Now, two line segments can have the same length and direction, and they would be equivalent. So if I were to carefully copy AB down here and have it be the exact same length and go in the exact same angle here, if I want to call this CD, and even though it's in a different spot, the vector AB would be equivalent to the vector CD, and that's just because the length and the direction are both the same, or the magnitude and the direction are both the same. Vectors usually are denoted by lowercase letters in boldface. Oh, and I haven't even said that these are vectors. These are vectors. These directed line segments are vectors. So vectors, or in other words, these directed line segments, are denoted by lowercase, boldface letters. Like, if you read it in a textbook, it would be like a U or a V. They're in boldface, W. So anything that is in bold, lowercase, is usually they're talking about a vector. Now, a vector in a plane can be represented by 2 points. Or in the plane. Perhaps you will have point P at 1, 2, point Q at 4, 4. And if I want to know what the magnitude of this vector PQ is, so PQ is a vector which has initial point P, terminal point Q. So if you want to find the magnitude, you can do a little quick sketch of this. Over 1 up 2, over 4 up 4. So here would be the vector over here. If you want to find the magnitude of that, you can just use the Pythagorean theorem. A squared plus B squared equals C squared. So this C, if you take the square root of A squared plus B squared, you'll get the magnitude of that. So if you want to get the magnitude of PQ, you can find that with the square root formula, and you can just use the distance formula, which is x1 minus x2 squared plus y1 minus y2 squared. It doesn't matter which goes first, the x1 or the x2 or the y1 or the y2, because when you square them, you're going to get the same answer. So there's your magnitude formula. So in this case, the magnitude of PQ would just be equal to 1 minus 4 is negative 3 squared. 2 minus 4 is negative 2 squared. So that's the square root of 9 plus 4 is 13. So we'd have the square root of 13 be the magnitude of that. Now the direction is just an angle that this would make with the horizontal line here, and we'll talk about the direction, calculating the direction, but it has to do with trig. But before we do the direction, before we talk about the direction, let's talk about a component form of a vector. Component form. Okay, a component form of a vector is this. If you move any vector so that its initial point moves back to the origin, then the terminal point would define what the component form of the vector is. So let's talk about a vector in standard position. Because the vector in standard position will get us to the component form of this vector. So a vector in standard position has its initial point at the origin. So if its terminal point, so if you move this back to the origin, then of course the terminal point would have to move in the same horizontal and vertical direction. So let's say if its new terminal point let's call it v1, v2 for vector. If its new terminal point, so you move that back to the origin, it'll have a new terminal point, is, let's say it's equal to that, then the component form is denoted with this. This is called a chevron. It looks like a great big less than symbol, but it's just called a chevron v1, comma v2. So this is just the new terminal point after it's been moved back. So here is the component form. Component form means the initial point is at the origin, and then this is the new terminal point. So v1 and v2 are called components of the vector v. And I'll denote v with a bold face type there. All right, and now it's a lot easier to calculate the magnitude of this vector, because the magnitude of v, this is boldface v, is just equal to the square root of v1 squared plus v2 squared, because if the initial point is 0, 0, it would just be v1 minus 0 squared plus v2 minus 0 squared, so you get that. So it's a little bit easier to find a magnitude if you get it in component form first. Now, if the magnitude of a vector is 1, it's called a unit vector. So there's the magnitude is equal to 1. It's called a unit vector. Okay, let's get an example going here. Let's say find the component form and the magnitude of vector v having an initial point at 4, negative 7 and terminal point, let's call it q. Let's have the terminal point be negative 1, 5. All right. So what we would have to do in order to move PQ, let's just take a look at where P and Q are. P is over 4 down 7. And Q is over 1 and up 5, so here's Q. So this vector looks like this. So in order to move this vector back so the initial point goes to the origin, you're going to have to move it to the left 4 and up 7. So what you're going to do is move this point to the left 4, so you're going to subtract 4 from negative 1, and then you're going to add 7 to 5. So what you can do is the component form of PQ, component form has chevrons here. So you can do Q1, let's call that Q1. Let's call this Q2. So it's Q1 minus P1. We'll call this P1. This is P2. Those are the components of the point P. We'll call this Q1, and this is Q2. So the component form Q1 minus P1, comma, Q2 minus P2. So the component form of this PQ is Q1, which is -1, minus P1, comma, Q2, which is 5, minus P2, which is -7. And just to simplify that, you will get -5, comma, 12. And that makes sense. Whoops, that's a chevron. That makes sense. If you move this point to the left 4 and up 7, you'd get back to -5, positive 12. So that is PQ in component form. Now let's say we want to find the magnitude. So the magnitude of PQ is equal to the square root of -5 squared plus 12 squared. And if you add 25 to 144, you get 169, I believe, which would give you 13. So the magnitude of that is 13. Now what we're going to do is talk about a linear combination. So this is just another way to represent a vector. Okay, a linear combination, what does that mean? Well, first of all, let's define two standard unit vectors. So here's the x-axis and here's the y-axis. And let's say this point is 1, 0. So here's a unit, this is one unit vector here, if this is the number 1. And then here's another unit vector here. And this is 1. So this is over 1 and this is up 1. So this vector right here, this unit vector with the terminal point at 1, 0 is called I. Just a lowercase I. It's not the imaginary unit I, but it's just I. Now this unit vector right here, maybe I should draw it in different colors so you can kind of see what it is. This unit vector is I, and this unit vector right here with the terminal point at 0, 1, this is the vertical unit vector. This is called lowercase j. So if you want to write a vector in linear combination, you're going to use I and j. So you're going to use I to represent the x or the horizontal component, and you're going to use j to represent the vertical or the y component. So if we wanted to take PQ up here, this is component form, but if we wanted to write this as a linear combination, we write it as -5I plus 12j. And all that is taking the x value and tacking on an I to it and the y value and tacking on a j to it. So this is linear. It's just another way to represent a vector. All right. You can add and subtract and multiply vectors by some number. It's pretty easy. All you do is add the x and the y components. For example, if we wanted to add the vector -3, 8, whoops, and 2, -1. Let's say the vector v is equal to that, and the vector u is equal to that. So we've got a v defined as this, a u defined as this. If we want to say v plus u, all we're doing is adding those two vectors. You just add the x's together. It's so easy. -1, -3 plus 2 is -1, and 8 plus -1 is 7. So you can add, you can subtract, you can multiply a vector by a constant. For example, if I want to say what is 10v, and this is a bold v because it means 10 times the vector v. 10v, just multiply those components by 10. So it would be -30, 80. So you can perform some arithmetic just like you do anything else. And then the last thing I want to talk about is direction angles. If you have a vector in component form, let's say it's at some point x comma y, that's where the terminal point is. The direction angle is this angle theta. So it's just like we did last year in Algebra 2. If you want to find this angle right here, you can just drop a perpendicular down to the x-axis. The height of this right triangle that's just been created, the height of this is y, the length, the base of this is x. And so if I want to find this, I just use tangent. The tangent of theta is y over x. So this direction theta is equal to the inverse tangent of y over x. Now you just have to be careful. You have to consider what quadrant you're in, because if you go outside of quadrant 1, then you have to pay attention to whether it's negative. This value is negative, and you have to use reference angles, but we'll get some more practice at that later. And I think that's about it. We'll just practice some of this tomorrow in class. So I think I just want to say pay attention to the quadrant, because you may have to use reference angles. So that's it. See you tomorrow.